Section 4.3 is greatest common divisors and least common multiples. Just kind of an extension of what we've been doing. We've been looking at divisors. We've been looking at mostly divisors, but we have talked at least briefly about multiples. And we're going to kind of take this a step further today. So just a little bit of vocabulary first. Greatest common divisor, or GCD, sometimes also called the greatest common factor, or GCF, is the greatest whole number that divides all numbers in your set of numbers. And we are finally going to define the word that I keep using, or the phrase that I keep using, relatively prime. Relatively prime are two or more numbers whose greatest common divisor is 1, i.e. they have no common factors other than 1. So the example we were just talking about from your homework, that was 3 and 4. 3 and 4 are relatively prime, even though 4 is not prime, right? But 2 and 6 are not relatively prime because they have a common factor 2. Now, there's one thing that I want you to realize, and I'll mention it again when we get to the other definition about least common multiples. The only way that this makes sense is if you realize the way we use English. This word greatest is an adjective that's describing divisor. Okay? So greatest common divisors, and just jot this down for yourself, are typically small numbers. And the reason that's true is because they're divisors. They have to divide what you've started with. So at the very biggest, they're half as big as what you began with. So what's the biggest divisor of 100 if you don't count itself? Well, 50. Okay, it's smaller than what you started with. So greatest common divisors are not big numbers, they're small numbers. We're going to work through, let me see, I can't remember how many it is. 1, 2, 3, 4, 4 different methods for finding greatest common divisors. Now, when we get to the test and when you get to your homework, sometimes they specify which method to use and sometimes they don't. So you do need to know what all 4 methods are and how to use them, but sometimes you get to make the choice on which one you use. Okay?
So GCD and GCF are the same?
They are. It just depends on the resources that you're using. You'll see them used interchangeably because a factor is the same thing as a divisor. Yes. And I will probably just move in and out of each one of them without even thinking about it because of my language and my familiarity with different resources is probably why. So you'll hear me use both. Okay, first method, intersection of sets method. And each method has its pros and cons. I'll try and mention those as we go through them. In this method, you list all the divisors of each value, and then you find the largest divisor that the values have in common. So, this works really well with younger kids because it's very concrete. You can make a list. As soon as kids know how to divide in their division facts, which is occurring, 3rd grade, 4th grade-ish, more concrete in 4th grade, you can do this with them. That's really nice. And you do see applications of this. Maybe it's not called GCF or GCD, but they're still using those ideas with them. But you're looking at this being sort of a middle elementary grades topic, okay? So what does it look like? And it also works really well, just generally speaking, the smaller your numbers are. If your numbers are really big, this could be very tedious, or it could be very easy to sort of overlook a divisor just because the numbers are larger, or maybe less familiar to you. So we're going to do an example. Our example is 12 and 15. Obviously, I chose small numbers on purpose because I told you this method works well for numbers that are small. So here's the idea. You start by listing all of the divisors that divide 12. You can list them in pairs if you like. I kind of like listing in pairs because then I don't forget things as easily. I might overlook it accidentally if I don't. So I would list like 1 and 12, 2 and 6, and then 3 and 4. And if you're sort of going up, like my 1, 2, 3, then you notice that the other divisors go down, 12, 6, 4. And you'll know that you're sort of at the end of the list because you get numbers that are too close together. There's nothing either in between them, or at least nothing in between them that divides the number. So it's kind of a nice stopping point to know I've found them all. We'll do the same thing for 15. So 15 is 1 and 15, and then what? I don't know why I put a fraction bar. Let's try that again. 1 and 15, and then what else? right? 3 and 5. And again, there's a number between 3 and 5, namely 4, but 4 doesn't divide 15, so then I know I'm done. So what you're doing then is you're looking at these two collections of objects. In particular, they're of course, are factors or divisors. And you just want to pick the biggest one in both lists. So what is the largest number that's in both lists? 3. So your GCF or GCD, whichever one you like to call it, is 3. Right? It's really concrete. A third grader, a fourth grader who knows division facts need only know that in order to do this problem. Okay? But if the numbers were quite large, this would be much more difficult. At least more difficult, depending on how large and how ugly the numbers were. So let's try another method that works maybe a little bit better as the numbers get larger. This is one of the very common methods that's taught middle grades, okay? Early middle grades. Still, all you need to know is division facts, but you usually don't do this with them until 6th grade-ish, okay? Prime factorization method. This is the one that I most strongly remember being taught. Maybe you will too, I don't know. To construct the prime factorization of each number, that's what we did in the last section in 4.2. Prime factors, factor trees, or division ladders, those kinds of things. And then find all the prime factors that are in common in both lists. Got to get them all. With the smallest exponent in either factorization. And then you multiply the results out. Find the product. And we're about to make our numbers much larger than last time. We did 12 and 15 last time. This time we're going to do 400 and 360. So I don't know about you, but I don't want to write out all of the things that divide 400. If I were doing it that other method, that would take a while. And I would probably, at least likely, forget something along the way. I'd probably skip one accidentally because there's a lot of them. So let's take a look at this method. And I'm going to do it with the division ladders that I showed you how to do last time, just to have more practice at doing that. So division ladders means that we take the smallest prime number that divides 400. So let's try. What's the smallest prime that divides 400? 2. And when I divide, I get 200. Can I use 2 again? Yes, so I do, and I get 100. Can I use 2 again? So I do, and I get, can I use 2 again? And I get, can I use 2 again? No. So then I go to 3, because 3 is the next prime number. Does 3 work? No. So then I go to 5, and does 5 work? Yes. And I know for this one in particular, you guys knew that already. I'm not trying to discredit that, but that's how you think about the problem. You just go step by step. And if you were writing this down then, you have 2, how many 2s? My goodness. 4 of them. And you have 5s. How many of them? 2 of them. So this is the factorization, prime factorization of 400. We're going to do the exact same thing with 360. So I'm going to be quiet and let you do 360. And then we'll make sure that everybody has the same thing. Okay, so you should have divided by 2 first. Did that happen? Good. What did you divide by second? 2 again to get 90, and then 2 again to get 45. And this is one of those places where you might be tempted to divide by 5, but that's actually not this process. It should be 3 next. This keeps them in order if you do think about it like that. Dividing by 3 would give me 15, and then I would divide by 3 again to give me 5. So I have 2 to the third, and then what? 3 to the second, and 5. And again, If you leave the dots out because they have powers, it's probably okay on this one. In general, if the powers are sort of not pairing, like there's not multiples of things, then you do need to make sure the dots are between them. Okay, so we've done basically step 1. Prime factorization of, in this case, both numbers. Second step is to list the prime factors that are in common. So what do we have common of the prime factors? They both have a 2 and they both have a 5. Okay, it's not just 2 times 5 though. That would be sort of shortcutting yourself. It would be ignoring step 3. Step 3 says to list each prime with the smallest exponent from either number. Okay, from any of your factors. So there's 4 2's here and there are 3 2's here. So what's the least number of 2's? 3. So that's the exponent on the 2. And then over here on the 5's, there are 2 5's here. How many 5's are here? 1. So what's the least number of 5's? 1. Now I'm going to write it with a power 1, but obviously you guys recognize that that doesn't mean anything in terms of it being different. It was just the same as 5. And the last step over here says that we're supposed to do what? Multiply it out. Find the product, okay? So 2 cubed is 8. 8 times 5 would be 40. So the GCD, or GCF, is 40. Okay? Who remembers that method? I don't mean like you could do it in your sleep, but you remember being taught that method. A couple of you, okay? This is the one that I remember. Maybe not in terms of this division ladder, but maybe in terms of factor trees. But this is how I remember being taught. Division by primes. This is probably my favorite method now. Having learned all these methods, I really like this one. Division by primes. You write the numbers in a row. You divide the numbers by a common prime factor to both or all of them. We could do this with 3 or 4 numbers, okay? And then you actually divide them all. And you keep repeating that process until there aren't any more numbers that divide both or all of your numbers. And then every number that you divide it by, you multiply them together. Okay, you ready to try them? In some ways this feels similar to the last method, but I think that it's a little bit more compact. It doesn't take as long. Because in all honesty, when we did all of this, we found a lot more information that we really needed to find the answer, right? We found complete factorizations for both numbers, and we really didn't use all of those details. We used some of it, but not all of those details. So this is sort of almost like, it's almost like overkill, right? I found more than I really needed to find, and I used the portion that I needed to use. So let's take a look at what this one looks like. We're going to put the numbers sort of beside each other, obviously a little space between them, but they're sort of next to each other on a quote-unquote row. And it's going to look like the division ladder that I did before, but I only get to divide the numbers if they're both divisible by the same thing. And we're doing primes still because it's the division by primes method, right? So what is the smallest prime number that divides both of them? It's a 2. What is 410 divided by 2? And 360 divided by 2. Okay. So even though 180 still divides by 2, I can't do that again because 205 doesn't. How about 3? Will 3 divide both numbers? Nope, because 205 doesn't work. How about 5? Yeah, because it ends in 5s and 0s. So what's 205 divided by 5? Okay. And 180 divided by 5. Fantastic. Now we kind of run into a problem here. In fact, we can, if you weren't sure about 41, let's just focus on 36 for the moment. You know you can't use 2's or 3's because we've already tried and they didn't work before. 5's no longer work, right? And if you take a look at the number 36, the next number that would divide 36 in terms of primes would be what? 6, and it's not prime, right? But yeah, so we run into 6, and 36 is 6 times 6. So if you're sort of like, if you're thinking about like what we did over here where we listed them in pairs, we're at options at this point. There's nothing else that's going to work. Everything else is going to be composite. So, whoops, sorry, went wrong direction there. So we're done. Now, the reality is 41 is actually prime. Maybe you knew that, maybe you didn't. But the point when we got a prime number as well, we would know, or at least a prime number we knew was prime, we would also know we were done. So the GCD then, the GCD is the product of everything we divided by. So in this case, it's simply 10. If we divided by 2 3 times, we'd multiply 2 times 2 times 2. However many times we divided, everything we divide by is part of the GCD. See, I kind of like this one. I know this didn't have as much in common as the last example that we did, but I only divided by the things that mattered instead of getting all of them completely divided down to their primes. I kind of like that. The next one is the most hidden in terms of seeing where or why it works, maybe. You're most likely to see this method used in probably some kind of an enrichment math class. For example, Shawnee Middle School has a math enrichment class. Kids who are good at math really enjoy it, enjoy puzzles, things like that, might encounter this. I do have one of our previous elementary ed majors who's teaching middle school over there, and she's taught that class. So this is sort of maybe a less typical curriculum kind of one, but I want to make sure you've seen it. It's called the Euclidean Algorithm. So what you do is you divide the larger number by the smaller one, and you take the previous divisor and divide it by the remainder of that problem. You repeat the steps until you get a remainder of 0. The last thing you divide it by is your greatest common divisor. So this is what we call a recursive process. It means you have to use what you did in step 1 in order to be able to get step 2 right. Okay, and then you have to use what you did in step 2 in order to continue on into step 3. It's called recursive. So it's really not hard to do, but it's really weird to write down. So let me show you how it works with an example. We're going to do 72 and 126. So what it says we're supposed to do is to divide the larger number by the smaller one. All right, so we'll do 72 on the outside, 126 on the inside. How many times will 72 go into 126?
1.75.
What did you say? Okay, so whole number times 1, right?
Yeah.
Okay, good. Yeah. And then we would subtract. So think old school, like elementary, first time learning to do division kind of stuff. 126 minus 72, what does that give me? 54. Okay, so what we're going to do next is we take the remainder and we take the divisor. Those are the two pieces we take. Have no care at all about what came out of this. This one at the top means nothing, okay? It's the remainder and the divisor. And I take the divisor and it becomes the dividend. It becomes the part that's underneath the division sign with the remainder on the outside. The remainder is now my divisor. The divisor is now my dividend. And I do it again. How many times will 54 go into 72? 1. 1 times 54 is, of course, 54, and the answer is not always 1, by the way. It doesn't have to be. It just happens on this one. What's the remainder? 18. And I do it again. The 18 is now on the outside, and the divisor, which was 54, is on the inside. How many times will 18 go into 54? 3. What's 3 times 18? It's actually 54. So at the point when I get a 0 here, I'm done. This 0 tells me I'm done. And the answer is the last number I divided by. Okay. So the GCD is 18. It's the last number I divided by. Okay, any questions on those?